Hi everyone, I'm Lap-Loi Chung from National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Chung University. Welcome to the course Seismic Evaluation and Retrofit of Structures, offered at the Department of Construction Engineering, National Taiwan University of Science and Technology. The lecture here is Simplified Pushover Analysis 1. From pushover analysis, we have the force relationship of a structure. And this analysis has been simplified so that it can be manipulated by hand. This is my name in Chinese, Zhong Li Lai. Here are some terminology. The first one, simplified pushover analysis. From pushover analysis, we have the force relationship of a structure. That is, the base shear of the structure versus the roof displacement of the structure. And this analysis has been simplified so that it can be operated by hand. In order to simplify the analysis, we have to make some assumption. The assumption is shear building, and in shear building, the beam is assumed to be very rigid so that the rotation of the beam can be neglected. And all the information of the lateral displacement of the structure is mostly contributed by columns only, or vertical members only. In addition to shear failure and flexural failure, there's one more failure mode called flexural shear failure mode. And in this failure mode, it is initiated in terms of fracture. And then at some displacement, some deformation, it changes from flexural failure to shear failure. Therefore, it's called flexural shear failure. We also have to have the force displacement in story level. That's the relationship between story shear force and interstory drift. And capacity curve is the result from pushover analysis. That's the relationship between base shear and roof displacement. Pushover analysis. In pushover analysis, we would like to find the relationship between lateral force and lateral displacement of a building. And the analysis has been simplified under the assumption of shear building. By this assumption, the beams is assumed to be very rigid, so that rotation can be negligible. And then the lateral force and the lateral displacement of the building is mostly contributed by columns. In simplified pushover analysis, there are totally 3 stages. The first one is to find the relationship in the member level. That's the relationship between lateral force and lateral displacement of those vertical members. In the second stage, we would like to find the relationship in story level. That's the force relationship in story level. That's the relationship between lateral force or story shear force and lateral displacement or interstory drift for the stories. And from the story information, we can find the relationship in the structural level. That's the relationship between lateral force or base shear force and the lateral displacement. That's the roof displacement of the structures. Okay, we begin with the member level first. Under flexural failure, we assume that the column deformed in double curvature. That means that the inflection of the deformation located at the mid-height of the column. Therefore, the lateral force due to flexural failure equal to 2mn divided by hc. Vm equal to 2 mm divided by HC. And mm is the moment strength of the column, and HC is the clear height of the column. That means that at the bottom of the column, the moment has been developed. Also, at the top of the column, the moment is also developed, so that we have 2 mm at the bottom and at the top, divided by HC, and then we can have the lateral force of the column. Under shear failure, the shear strength of the column Vn is provided by Concrete Structure Design Code, equation 4-2. Vn equal to Vc plus Vs. Vc is the shear strength contributed by concrete, and Vs is the shear strength contributed by steel. That's the transverse reinforcement. And from Concrete Design Code equation 4-4, we can have the shear strength contributed by concrete. Vc equal to 0.53 times 1 plus Nu divided by 140 Ag times square root of Fc prime times Bw times D. And Nu here is the design axial load. That's the axial load under dead load and 1/2 live load. And it is positive for pressure and negative for tension. And Ag is the gross area of the column cross-section. That's the total cross-sectional area of column. And Fc prime is the compressive strength of concrete. And Bw here is the width of the column, and D here is the effective depth of the column. And from a Concrete Design Code, equation 4-15, we can have the shear strength contributed by steel. Vs equal to Av times Fyt times D divided by S. And Av here is the cross-sectional area of transverse reinforcement in spacing S. And Fyt here is the yielding strength of the transverse reinforcement. And S is the spacing of the transverse reinforcement. If Vm less than Vn, that's the lateral strength of the column due to flexural failure, is less than that due to shear failure, then the column fails in flexural or flexural shear failure. And if Vn less than Vm, that's the lateral strength of the column due to shear failure, is less than that due to flexural failure, then this column fails in shear. Therefore, from the value of Vm and Vn, we can determine the column failure mode. If Vm is less than Vn, then the column fails in flexural or flexural shear. And under this failure mode, the force relationship of the column can be fully described by 4 points. Point A is the origin, delta equal to 0, V equal to 0. Point B, delta equal to delta Y, V equal to Vm, and Vm equal to 2 mm divided by HC. And point C, delta equal to delta Fs, and V equal to Vm. And at point D, delta equal to the maximum of delta Fs and delta A, and V equal to 0. And delta Fs is the lower bound of delta A, because in the force displacement relationship, the displacement is ever increasing. Therefore, delta A cannot be less than delta Fs. And under flexural shear failure mode, Vm is less than Vn. That means that the lateral strength due to fracture is less than that due to shear. When the displacement is small, it's linearly related. And at some point, we can have the maximum or the bending strength. And the bending strength keep constant for some time when the displacement is large enough. At this point, the failure mode changes from shear failure mode to flexural shear failure mode. And at this point, the bearing capacity of the column lost. Therefore, the displacement, the force displacement relationship of a column under flexural shear failure can be described by 4 points. The first one, 0, 0. The second one, delta y Vm. The third one, delta Fs Vm. And the last one, delta A 0. Okay, and how do we calculate the coordinate of these points? And we move to point B, and delta equal to delta y equal to Vm divided by Kc, and V equal to Vm equal to 2mm divided by Hc. And Kc is the column flexural stiffness, equal to 12 times EIC divided by Hc cubic. And due to cracking, the flexural rigidity of the column is reduced to 35%. Therefore, EIC equal to 0.35 times EC times IG. And EC is the concrete elastic modulus, equal to 15,000 times square root of FC prime. And IG is the second moment of the column of the total cross-section area. Then IG is the second moment of column of the gross cross-sectional area of the column. And we move to point C. At point C, delta equal to delta Fs, V equal to Vm equal to 2mm divided by Hc. According to some test results of the columns, people can come up with the formula to calculate delta Fs. And delta Fs divided by Hc is given to be 3 divided by 100 plus 4 times rho double prime minus Vm, small vm, divided by 133 square root of Fc prime minus Nu divided by 40 Ag Fc prime. And 1 over 100 is the lower bound of this value. That means that delta Fs divided by Hc should be larger than or equal to 1 over 100. If the value from this formula is less than 1 over 100, then delta Fs divided by Hc is assigned to be 1 over 100. And rho double prime here is the volume ratio of the transverse reinforcement. Rho double prime equal to Av divided by Bs. If we multiply D and multiply D for the numerator and the denominator, therefore the numerator becomes the volume of the transverse reinforcement, and the denominator becomes the volume of the column in spacing S. If rho double prime is larger, that means that we have more transverse reinforcement. Then the deformation, the displacement becomes larger. And AV is the shear bar cross-sectional area in spacing S. That's the cross-sectional area of transverse reinforcement in spacing S. And B is the width of the column. And Vm here, small vm, is the shear stress equal to Vm divided by Bd. Vm is the lateral strength due to flexural failure. If shear stress is large, then the displacement becomes less. And D here is the effective depth it can be assigned to be 0.8, 80% of the total depth, and H is the column depth. And NU here is the design axial force. When the design axial force becomes larger, the displacement capacity becomes less. And then we move to point D. Point D equal to maximum of Fs and delta A. And then V equal to 0. And from lots of experimental results, people can come up with a formula for delta A divided by HC equal to 4 over 100, 1 plus tangent square theta, divided by tangent theta plus NUS divided by phi S AB FYT DC tangent theta. And theta here is the angle between the crack and the horizontal line. Theta equal to the minimum of 65 degrees and arctangent of HC divided by H. And NU is the design axial force, S is the spacing of the transverse reinforcement. The higher the axial force, the lower the displacement capacity. And phi S is the reduction factor due to 90-degree hook, because for existing structure, 90-degree hook for the transverse reinforcement is very common. And phi S is a function of mu, and mu is the ductility ratio. There's mu equal to delta Fs divided by delta Y. Delta Fs from point C, and delta Y is the information from point B. When ductility is small, that means that the deformation is small, phi S is larger, equal to 1. When ductility is higher than 6, ductility ratio is higher than 6, and phi S is reduced to 0.7. And linear interpolation is used to find out phi S when mu is higher than, larger than or equal to 2, less than 6. And AV is the cross-sectional area of the transverse reinforcement. Larger AV, smaller than the denominator becomes smaller. Then the deformation capacity becomes larger. And FYT is the yielding strength of the transverse reinforcement. And DC is the depth of the core concrete. If Vn less than Vm, then shear failure is controlled by shear failure. And under shear failure, the force displacement relationship of a column can be fully described by 3 points. Point A is the origin, delta equal to 0, V equal to 0. Point B, delta equal to delta S, V equal to Vn. And point C, delta equal to maximum of delta S and minimum of delta A and 0.04 HC. Therefore, once we have delta A, we compare with the delta S, and delta S is the lower bound of delta A, and 0.04 HC is the upper bound of the delta A, because under shear failure, the displacement cannot be that large. Therefore, we have the upper bound 0.04 HC. And for pushover, for force displacement relationship, the displacement is ever increasing. Therefore, delta S cannot be larger than, or delta A cannot be less than delta S, so that we have delta S as the lower bound for delta A. Okay, under shear failure, the lateral force due to shear is less than the lateral strength due to fracture. When the displacement is small, the relationship is linear. Then we have the stiffness K. Even though it is a shear failure, but the displacement is contributed largely by fracture. So that the K here is the fractional stiffness. When the shear strength is achieved, the strength degrades very quickly to delta A. And in delta A, we have the lower bound, delta S, and we have the upper bound, 0.04 HC. Okay, point A is the origin, and point B, delta equal to delta Fs. Delta equal to delta S equal to Vn divided by HC, and Vn equal to Vc plus Vs, and HC equal to 12 EIC divided by HC cubic, and Kc has been mentioned previously, and V equal to Vn equal to Vc plus Vs. And then for point C, delta equal to delta S, maximum of delta S and minimum of delta A and 0.04 HC. Delta A divided by HS is similar as before, equal to 4 over 100 times 1 plus tangent square theta divided by tangent theta plus NUS divided by phi s, and phi s here, because the ductility ratio is equal to 1. Therefore, phi s here is 1, no reduction due to 90-degree hold. And AB is the cross-sectional area of the transverse reinforcement, and FYT is the yielding strength of transverse reinforcement. DC is the depth of the core concrete. Okay, there are totally 7 columns here, number 8 to number 14. But from this graph, only 3 curves. That means that there are only 3 different columns. Then we have the force relationship of 3 different columns. In the horizontal axis, we have the lateral displacement of the column, delta Cj. In the vertical axis, we have the lateral force, Vcj. So far, we have talked about the force relationship in member level. Then we move to story level. The force relationship of a story. VFI is the story shear of floor I, and VFI is the interstory, delta Fi is the interstory drift of floor I. Under the assumption that the slab or the diaphragm is so rigid in plane, therefore the distance between any 2 columns at the same floor remains the same before and after deformation. And under this assumption, delta Fi, that's the interstory drift of floor I, equal to delta Ficj, and delta Ficj is the interstory drift of the column I in floor J, column J in floor I. Delta Fi is the interstory drift of floor I. That's the displacement of I plus 1, that's the upper floor, relative to the I floor, that's the current floor. And in a floor or in a story, columns are considered as springs arranging in parallel, so that the story shear is the summation of all column shear at the same displacement, so that we have VFI equal to the summation J, VFJ, Cj, and VFI is the story shear of floor I, and VFI Cj is the shear or the lateral force of column J in floor I. And here is an example of the force displacement relationship in the story level. That's the first floor, story shear, and interstory drift. In the horizontal axis, we have interstory drift delta F1. In the vertical axis, we have story shear VF1. And the curve here is the relationship between story shear VF1 and inter-story drift delta F1. Then we move to the third stage. That's we would like to find out the capacity curve in the structure level. And structural capacity curve is the relationship between base shear and roof displacement delta RF. If the first story is the base, then the base shear VBS is the first floor story shear VF1. Then we have VBS equal to VF1. And here we take a two-story building as an example. And how about the distribution of the seismic forces? And F2 is proportional to the weight of the second floor and the elevation of the second floor. Therefore, F2 equal to W2 H2 divided by W2 H2 plus W3 H3 V equal to alpha 2 V, and alpha 2 equal to W2 H2 divided by W2 H2 plus W3 H3. And the seismic force applied at the roof is proportional to the weight of the roof, that is W3, and the elevation of the roof, that is H3. Therefore, F3, the seismic force applied at the roof, equal to W3 times H3 divided by W2 H2 plus W3 H3 times V equal to alpha 3 V. Alpha 3 equal to W3 H3 divided by W2 H2 plus W3 H3. And we have the relationship here, alpha 2 plus alpha 3 equal to 1. F2, F3 are the seismic forces applied at the second floor and the roof. W2, W3 are the dead loads or weight of the second floor and the roof. And H2, H3 are the elevation of the second floor and the roof respectively. And V is the base shear force. Okay, the base shear VBS equal to VF1. And VF1 is the first story shear, VF1. And from the relationship between the force relationship of the first floor, once we have VF1, then we can come up with the first story drift, delta F1. And once we have VF1 from the vertical distribution of the seismic force, we can have the second story shear, VF2. VF2 equal to F3 equal to alpha 3 times VBS. That's alpha 3 times VF1. Once we have VF2 from the force relationship of the second story, then we can have the second story drift, delta F2. Once we have delta F1, the first story drift, delta F2, second story drift, the summation of these two becomes roof displacement. Once we have the base shear here and roof displacement here, and the relationship between base shear and roof displacement becomes the capacity curve of the structure. Okay, in a building, all stories can be considered as springs arranging in series. Therefore, the roof displacement is the summation of the inter-story drift from the lowest level to the highest levels. Therefore, delta roof equal to delta F1 plus delta F2. And here's an example for a capacity curve. From the capacity curve, we have the relationship between base shear, VBS, and roof displacement, delta RF. And here's a procedure for simplified pushover analysis. Step 1, we have to determine the failure mode of the columns. If Vm is less than Vn, then we have shear failure. If Vn, we have flexural shear failure. If Vn is less than Vm, then we have shear failure. And according to the failure mode, we can find out the force relationship of the column. That's the relationship between lateral force, Vfi Cj, and lateral displacement, delta Fi Cj. And according to the assumption of rigid diaphragm, then we have delta Fi. That's the ice floor inter-story drift equal to delta Fi Cj. That's the lateral displacement of all the columns in that floor. And Vfi equal to the summation of all column lateral force. Therefore, Vfi equal to summation J, Vfi Cj. And step 4, corresponding to the first story shear, then we can have the base shear, VBS equal to VF1. And from the relationship, force displacement relationship of the first floor, once we have VF1, we can have the first story displacement, inter-story displacement, delta F1. And then we move to step 6. According to the seismic force distribution, vertical distribution of seismic forces, once we have VF1, first story shear, then we can have the second story shear, VF2 equal to alpha 3 times VF1. And then we move to step 7. According to the force displacement relationship of the second floor, once we have the story shear, second story shear, Vf2, from this relationship, we can have the second story inter-story drift, delta F2. Once we have delta F1, inter-story drift of the first floor, and delta F2, inter-story drift of the second story, then the summation of these two becomes the roof displacement. So far we have the base shear, VBS, and roof displacement, delta RF. The relationship between these two becomes the pushover curve. That's the relationship between base shear against roof displacement. And here are some references. And videos are available for simplified pushover analysis. And also videos are available for simplified detailed evaluation. For simplified detailed evaluation, for preliminary evaluation. Okay, in this lecture, in order to find out the pushover, in order to conduct pushover analysis, it has been simplified so that it can be manipulated by hand. There are three stages for simplified pushover analysis. The first one is member level. We have to find out the force relationship of those vertical members, such as columns. There's Vfi Cj versus delta Fi Cj. And the second stage, we have to find out the force relationship in story level. That's the relationship between lateral force and lateral displacement, Vfi versus delta Fi. And delta Fi equal to delta Fi Cj, according to the assumption of rigid diaphragm. And Vfi equal to summation of Vfi Cj. And from the story level, we can move to the last stage. That's the building level. And in building level, we would like to find out the force relationship of a structure. That is V base shear against delta roof. And V base shear equal to VF1 if the first floor is the base. And delta roof equal to the delta F1 plus delta F2. And from this relationship, there's the capacity curve of the building. That's all for this lecture. Thank you. See you next time. Bye-bye.